I grew up in the steel town of Gary, Indiana. And just to the west of Gary, Indiana is another small town called Whiting, Indiana, which had a number of oil refineries. And my dad worked in an oil refinery, and he always encouraged me to work for an oil company because they had the money and it was a fun place to work. And I liked fluid flow and hydrodynamics. In the backyard, I used to dig trenches in the yard and to get the water out, to flow down trenches. And so that was always of interest to me. And it just seemed natural. Oh, the other thing is when I was young, I used to do doodles with arrows going here and there. Now I do doodles, but it's process going here, process flow going there. So I do the same thing. So getting into the oil and gas facilities seemed like just a natural thing to do. It was something that I found very interesting. Everything was very logical. There was a lot of math involved, and I enjoyed the math. I had a background in physics, so you have to have the math right, you have to have the physics right, and you have to understand the chemistry. And I still follow those same principles in my work today, because when you're working in facilities, you have to be sure that you're getting the physics right before you go after the chemistry. And hydrodynamics and fluid flow is a very important part of what I do. But my real entry into the industry to work in oil and gas facilities was because Unocal had a platform where they were having difficulty transferring heavy oil from the platform to shore. The pipeline pressure drop was much too high. And I was in the Unocal research division, and they needed to have someone who knew something about viscosity that could help them out. And since I knew about viscosity, I was asked to help out with resolving the problem. I also knew about something called core flow, where you could take a heavy oil with a little bit of water around it, and you can flow that through a pipeline and reduce the pressure significantly. So I suggested that they do that and gave them a method that would be very simple to implement, which they did, and it worked very well. And then I continued in the oil and gas facilities and production business after that. The development of water treatment systems for produced water really came about because of environmental regulations. The first technology that was implemented was hydrocyclones, which in some areas of the world worked very well to remove oil from the water. In other areas of the world, it did not work all that well. Hydrocyclones have water coming in near the top. It's a cylindrical top. The water comes in tangentially and circles around, generates very high, what we call G-forces. And because the oil is lighter than the water, the oil will tend to go to the center of the fluid in the hydrocyclone. The water goes to the outside. And then in the center of the hydrocyclone, what naturally forms is a core, of a low-pressure core that the oil moves into, and it's taken out the top of the hydrocyclone, leaving the clean water to go out the bottom. And so you take advantage of between 1,000 and maybe 2,000 times the force of gravity spinning around for 3 to 5 seconds is all it takes for the oil to separate. And then you can pull that out the top. One of the things that happens that people don't quite understand often is that small solids, even though those solids are supposedly heavier than water, will stick with the oil and they'll actually go out with the oil. So the reject that we call from the hydrocyclone is not only oil, but also some trace mineral solids. And recycling those back into the process is a problem. And that's one of the reasons why early installations of hydrocyclones were causing problems, was because of this recycle stream. They would be taking the contaminants out of the water with the hydrocyclone, putting it back in the separator, and sending it right back through the hydrocyclone again. They didn't have any way to take those contaminants out. Okay. So then the underflow, the clean water from the hydrocyclone, was in most cases, especially in U.S. waters in the Gulf, the water is still not clean enough to go overboard. So gas flotation then was a key part of the development of water treatment systems. I had some familiarity with flotation because my first industrial job was actually with a minerals company, Kennecott Mining and Minerals, and they used flotation in their processes for minerals recovery. So I understood the concepts of gas flotation. And so I was able to work on the hydrocyclones and on the flotation cells and the equipment. And then later on, I developed enough expertise to work on the design of the upstream equipment and the overall process systems. And in the flotation cell, small gas bubbles are generated that will float to the surface, and they will the gas bubbles will either attach themselves to oil droplets or oily solids, or as they rise, the oil droplets or the oily solids will follow the gas bubble to the surface. On the surface, they are captured and then removed, skimmed off either by use of paddles or by just skimming into a trough and taken out of the flotation cell. And they're generally in horizontal flotation cells. There are 4 stages of flotation, and this is just a carbon copy of what's done in the minerals industry. And so they will clean the water 4 times, and the water then is clean enough to go overboard. Now, initially, the use of polymers to help with the flotation was not well understood, but after a number of years, and I would say it probably took a good 10 years for the chemical companies to understand what kinds of polymers to use in the right situation in order to remove these contaminants in the flotation cell. But then the water, they set the environmental regulations in the U.S. were actually set based on the capability of flotation cells to remove oil from the water. And that's how the 29 ppm, well, initially it was 42 ppm average and 72 ppm max. Now it's 29 ppm average and 42 max. But most companies will maintain their water quality at less than 20 ppm residual oil. No one anymore is happy with 20 or 25 or something above 20. And in many companies, it's in the low teens. It's in the 10 ppm range. So that technology, although physically it looks the same, works a lot better than it used to. Now, since those early days, and over time, I've developed a lot more understanding of the physics of the process as well as the chemistry, and also the fluid flow patterns through flotation cells are very important to understand. That's where we have used computational fluid dynamics in order to model the flow through flotation cells, and that has helped us to improve the design of flotation cells as well. And that's another reason why this equipment, this technology now works a whole lot better than it used to. I remember the day that my boss, there were several of us in the hallway, and my boss comes in and says, Unocal Thailand has some problems with mercury in their water. Does anybody know anything about mercury? Everybody scurried into their offices, and I was the last man in the hallway. And I said, well, I know something about copper because I worked for a copper company. He said, that's good enough. It's your problem. And so then I was assigned the problem to work on the issue of mercury in the produced water. And the first thing then I found out it was not just mercury, it was also arsenic. Well, I understood mercury chemistry actually pretty well, but I did not understand the arsenic chemistry. But fortunately, I had a friend chemist who did. So I contacted him, and rapidly he brought me up to speed on arsenic chemistry. So we went out to the Gulf of Thailand, and at the time I had a research lab, and I had trunks of laboratory equipment that they would send out to the platform, and I would spend 2 to 4 weeks at a time working on the water out there, first to try to understand on a fundamental basis what was the issue. What was the form of mercury present? What was the form of arsenic present? And therefore, how could we take it out? Well, it turns out that the mercury was present as elemental mercury. Now, everyone was assuming that it was water-soluble mercury, but that was not the case. And that was a difficult cell job, but the way I did that was to filter the mercury out of the water. If you can filter the mercury out, it can't be dissolved. And then by a series of filtrations, we were able to determine what the droplet size was for the mercury. And it was all pretty small, but it pretty much filtered out on a 1-micron filter. And so then we also determined that these very small mercury droplets could be removed in a hydrocyclone. So that was the first step, was in the hydrocyclone. And then the second step was flotation. So whatever didn't get taken out in the hydrocyclone was taken out in flotation. Now, mercury is very heavy. And so you might think, well, wait a minute, wouldn't the hydrocyclone send the mercury with the water? Because the water is heavier than the oil. Oil is going to the middle. Why is that mercury going to the middle? Because it was very small droplets, 1 micron or less, and it was being associated with the oil. And so the droplets coated with oil and associated with other oil were light enough together to come to the center. And so we removed the bulk of the mercury in the hydrocyclone, which was counterintuitive. Okay? The droplets being heavy should have gone to the outside. Nope, they went to the middle. And I actually took a test hydrocyclone unit out. Because of my previous work with hydrocyclones, with the hydrocyclone companies, I had friends there. They would lend me equipment that they wouldn't lend other people because they knew that I wouldn't do it incorrectly. I understood the physical principles involved. So they would lend me equipment, and I could take it out there. Then in the flotation cell, again, because the mercury droplets were A, small, and B, hydrophobic, they would come out as long as I used the correct polymer. I could take them out in the flotation cell. So we were able to reduce the mercury in the water from, several hundred parts per billion, not million, but billion, down to less than 10 parts per billion. Now, at the time, and the reason this was important for Thailand is the Gulf of Thailand is a very important fishery. And Thailand is the 6th leading seafood export country in the world. And so if their fish that they were catching in the Gulf of Thailand were perceived to be contaminated, they wouldn't be able to sell that fish. So it was very, very important that we take it out. Toxicity or not, it was a commercial and economic that commercial and economic importance to the Kingdom of Thailand. Well, the arsenic, then it turns out we had to oxidize the arsenic from the +3 to the +5 state. Again, you had to understand the chemistry. Then we would precipitate the arsenic out along with some iron, and that we could take out in the flotation cell. Okay, so we had to put in an oxidant to oxidize the arsenic. So now we had a problem, because if we put in the oxidant and oxidize the mercury, it would not come out in the float cell. But we had to put in enough oxidant to oxidize the arsenic so it would come out in the flotation cell. And we found that there was a certain level of what we call oxidation reduction potential, or ORP, that would allow us to oxidize the arsenic but not oxidize the mercury. We constructed a pilot plant on the platform. After demonstrating this in principle, we constructed a pilot plant on the platform in the Gulf of Thailand, and I have to really compliment the Thai engineers because they really had to go out on a limb to encourage this to happen, to fund it and everything. And we operated that pilot plant for a total of about 6 weeks, and all of the commercially applied process conditions resulted from one afternoon of testing. We tried this and it sort of worked and didn't, and tried this and it sort of worked. One afternoon, we had the brilliant idea of controlling the oxidation reduction potential. We did the control the conditions through the hydrocyclone, through the flotation cell. We got a very nice set of data, and we said, okay, if you do this, it will work. And so that was the basis of design for the water treatment system that was actually installed on the platform, and it worked as advertised. Now, at the time, the Kingdom of Thailand was considering environmental regulations for allowable arsenic and allowable mercury in the water. They did not have regulations. They just knew that it shouldn't be there. So based on our work, and in Unocal, Thailand had a good relationship with the government. I mean, a very supportive relationship. It wasn't adversarial. It was very supportive. The Thais then adopted regulations based on what the technology would do. And then Malaysia followed suit and Singapore followed suit. So less than 10 parts per billion on mercury is the pretty much standard now for Southeast Asian mercury discharge. So that was kind of nice to be able to, develop and see that implemented. NATCO, another one of the challenges was to design separators, long horizontal vessels, that could be installed and work effectively on floating platforms, because this was just the early days of putting vessels on FPSOs and on floating platforms, spars and whatnot. And so, especially under storm conditions, those will slosh around and it totally messes up the oil-water separation. You can imagine, things are sloshing back and forth this way, and there are 6 degrees of freedom for the motion. And so you had to control that motion within the separator. So we started doing research with computational fluid dynamics on the use of perforated plates in separators in order to dampen out the movement of the water in the separators and maintain the oil-water separation. And then as the oil would flow over a weir, to the oil process, we didn't want any water flowing over the weir. We didn't want any oil going out with the water. And so each vessel, each platform or FPSO had its own environmental conditions. So what the end user would provide us with was all of the motion conditions, the roll, the pitch, the heave, everything. And each one had a different period of motion. So this one might have a 15-second, this one might have an 8-second, this one may have a 6-second. So it was interactive. And what the engineer that was doing our computational fluid dynamics for us at NATCO was able to do was to develop an algorithm that would allow us to move the separator with all these degrees of motion completely independently. So we could watch the sloshing develop. And then we could install in the model the perforated plates here, there, run through the simulation, which sometimes took up to 2 weeks to run, and see whether or not that was effective. And from watching it, we could say, oh, okay, we weren't so smart. So let's move this here and to put it there. Let's try it again. No, we still weren't so smart. So CFD is a very humbling technology. You think you know what's going to happen, and then it's like, whoops, doesn't happen. And then by trial and error, usually after 3 or 4 trials, we were able to have a pattern of perforated plates that would dampen out the motion and allow effective oil-water separation to take place even under storm conditions. And so these vessels were then placed on a number of FPSOs and floating platforms, and there really is the basis of design. There's a number of people who do this now, but in terms of the initial CFD work, some of the earlier work was done in our group at NATCO. Well, I think the biggest milestones were actually environmental regulations, because it forced the industry to do some things that it really didn't want to do because it required additional investment. But it forced everybody to do it on the same basis. So everybody had a level playing field. And therefore you did not have an economic driver that says, gee, I can't do this because my competitors will not have that cost. They will be more profitable, so their stock price will go up and mine will go down. Everybody had to deal with the same rules and regulations. And I think the other aspect of that is that once the initial shock of that passed and the industry accepted that they could do this, they could operate in an environmentally responsible manner without a major economic penalty, because again, the added oil recovery helped pay for the processing. They were then willing to take on other environmental challenges much more readily. They had viewed this one as with the water treatment as a very difficult one. A lot of people look at water treatment as a black box. They have no idea. It goes in there, comes out there. There's a few people in the world who understand what happens in between, but most of the people don't. Production engineers, they worry about the wells and the completion of the wells and how things come up the well, and it goes onto the platform, and they haven't a clue. So, you know, that's why us guys who work in facilities have to deal with this. But having dealt with that environmental regulation, then when it came to reducing gas emissions and handling other discharges, we said, sure, we can do that. It was not a matter of, no, that was impossible, we can't do it. No, we can do it. The environmental regulations that had the greatest impact were the limiting of the amount of oil that could be discharged along with the water, and the fact that the EPA did work with the oil industry in order to determine what level was best available technology, BAT, best available technology. And then as the technology improved, they they tightened the regulations. Now the industry is working with water quality, which is much better than that required by the regulators. In the future, we'll see some additional tightening of those regulations, but because of the toxicity testing that's required, there's no real hurry to tighten those regulations because the industry is working. You know, they're self-regulating. They're doing more than what is required, and the operators are very serious about this. Well, for two reasons: they take their environmental responsibility very seriously, but also, as long as the operator is following company policy, and the water is clean. But if the water gets dirty and it's you know, he's done everything right, he's doing what he's supposed to do, and he's making every effort to keep that water clean. If something happens, then you're given some leeway. If he is not following company policy and he's discharging water which does not meet the environmental regulations, he's actually criminally liable, and the company cannot even support his defense. All right, so they're very serious about this. Yeah. And then the other thing I think this did was that onshore, because now the technology developed offshore was not only effective but relatively inexpensive. That means the water onshore could be cleaned to a much greater degree, which allowed more water flooding to take place because we knew how to do this. And generally, we clean the water to a much greater degree onshore for disposal than we do offshore. Especially, well, in particular, if it's a matrix injection. If it's a fracture injection, what I tell people is you can't put the kitchen sink down, but you can put the bathroom sink down. You can put a lot of stuff down if you got fractures, but if not, then you have to clean that water. Now, the onshore regulation that's in place, certainly in California, and I think in most places, is when you're disposing of water, you're not allowed to fracture the zone into which the water is going. So you can't just pressure up to inject more water. So that means that water has to be clean. Okay? And one of the companies that I deal with, which I can identify because everything's public, this is in California, what used to be Thumbs, now operated by Occidental, they produce about 27,000 barrels of oil per day and over 1 million barrels of water per day. And they re-inject 103% of the total amount that they produce. So here they're injecting, they're producing 2.5% oil. They're injecting over 1 million barrels of water a day, and they do that economically because of the regulations started offshore. Now we know how to do that. We can do this onshore. And in a sense, this is where the industry is going. If you want to know where the major fields will be and what kind of water production they're going to have to deal with in the future, well, come visit us in California or certain places in West Texas where producing 2 or 3% oil is the norm. So the regulations have actually, I think, helped the industry. Well, I think one of the major challenges facing the industry in the future, and we're facing it now, is the resistance to the application of new technologies. There's a lot of misinformation or disinformation out there that has affected the perception of our industry. The operators have become environmentally conscious. Environmentally, they're much more careful than they were 30 or 40 years ago. And they have the technology and the capability of operating in a very clean manner. Not just environmentally friendly, but I mean totally clean manner. No discharge of oil onto the ground for any reason or whatever. So we can handle all that. But the perception is that we're still this wild bunch that just dumps whatever, wherever, whenever, and that just doesn't happen. When I tell people about my experiences offshore and how clean the water is, and the fact that the fish are out there, and fishermen come out and fish around the platforms because that's where the fish are, they're shocked. They're assuming that it's just a pool of oil around those platforms, and that's just simply not the case. It's squeaky clean out there. And then we even capture all the water, both onshore and offshore. If it falls on a facility in many places in California and it falls on a platform, that water is captured and cleaned along with the produced water. It's not discharged. So we can't just take rainwater and allow it to flow back off the platform or off the facility. We have to take care of it. The thing that's made working in the petroleum industry most meaningful to me is really the ability to keep learning new things. Because in my career, I've done a lot of different things, and the constant theme has been learning something new. So being able to learn new things and respond to a constantly changing series of challenges has been very interesting. It's one of the things that really keeps me involved. Problems were challenging, they were fun, and if you could come up with a solution, everybody was happy. The problems that came to me were the ones that no one else had solved. So if I was unable to solve it, there was no downside risk. But if I did solve it, everybody was delighted. And then oil and gas production facilities were all around the country, all around the world. I enjoy traveling, so I had kind of the best of both worlds. I could go here and there. I had very interesting problems to work on. I had great people to meet and to work with. And when I think about, well, what would I do when I'm retiring? I'm thinking, you know what? I'm kind of doing it.